problems. In other words, problems which have no Turing algorithm which decide them. Is that those two? Is that correct what I've just said? There's no algorithm that. Well, maybe that's too restrictive. I'll leave it to cannot be solved. Okay, so you'll get a feel for what kinds of problems cannot be solved, because we'll do example after example, and after a while you'll sort of generalize, and you start getting a feel. You'll start seeing patterns and so on about the nature, the commonality of problems that are unsolvable, hopefully. And the other technique you'll pick up, again hopefully, is how to actually prove that these problems are unsolvable. So they're the two things hopefully that you'll pick up. This section. I think there are only two sections in this chapter. Let's just check. Go to the index. Yeah, there are only two sections in this chapter. It's only about 18 pages or so, right? And the next chapter it's called reducibility. I won't go into what that means, but it's also a fairly shortish chapter. It has about 25 pages, and so the next one, 26. And then we get into part 3 on complexity theory. We get back to a monster chapter. It's like 48 or so. Nearly 50 pages long. And chapter 10, also on complexity theory, 47 pages or so, also nearly 50. So big section, part 3 after this one. All right. Okay, so now we get a bit more specific. We're going to introduce to you a language, and we will, as usual, because we've been doing this a lot, this previous section 4.1, trying to show that that language is decidable. Okay. Well, now we're going to present to you a language, and we will state that it's not decidable. But proving that that's the case, we'll have to wait to next board. But here's the language. Now we've done A DFA and we've done A CFG. Now these are just languages, right? So this language is what? It's the set of ordered pairs where the first member is a DFA and the second member is a string. Okay, and the properties that those members, that ordered pair, must have to be a member of the language is that the DFA accepts the string. Okay, and this language, something similar. It too consists of ordered pairs, and the first member of the ordered pair is a grammar, a context-free grammar, and the second member of the ordered pair is a string. And the property that that ordered pair must have to be a member of that set language is that the grammar can generate the string W. Okay? Right? So, and we know, we've done proof that both of these languages are decidable. In other words, there is a Turing machine algorithm. Well, same thing. There is a Turing machine that can decide both languages. So, in other words, the Turing machine will accept any member of the language and will reject any other string. Okay, for both cases. All right. Now these two languages, they're both. We've proven they're both decidable. Okay. How about this one? This is a new language we're going to call it ATM. Now it's got nothing to do with taking out money from an automatic teller machine. It's just the subscript TM is just Turing machine, and A here, capital A, well, it's just the language. And so you can probably guess what ATM is. It would be the language where, analogous to these two. So the members of this language would be, again, ordered pairs, okay? And the first member of the ordered pair would be a Turing machine, right? TM. Whereas before it was an finite automaton, a DFA, or a grammar. Well, this time the machine, it's a Turing machine. Okay, the first member of the ordered pair, and the second member of the ordered pair is string. Yeah, a string. Okay, and the condition that that ordered pair is, the property that that ordered pair must have to be a member of this language is that the Turing machine decides? Now wait a minute, I've got to be careful. Accepts. Actually, I'm a bit fuzzy on that, what it actually does. Well, that'll become clear next session. I assume, for the ordered pair, the property that that ordered pair is a member of the set is that the Turing machine accepts the string. That would be my guess. Okay. Anyway, that language, all those ordered pairs, all the members, that language ATM is undecidable. In other words, there is no Turing machine, there's no algorithm that can decide this. Meaning, there is no Turing machine that can look at any element of this language, and if it belongs to the language, that this Turing machine, we've got to be careful which Turing machine we're talking about. We're talking about the Turing machine that's trying to decide this language. Okay, call it U. Okay, so we're talking about this Turing machine U, big U, capital U. Okay, so if this U decides this language, what's it doing? Well, it would mean that it could. What's it doing? So any ordered pair of this language, this machine U would accept, and any other string it would reject. That's the notion of deciding, so that U would decide. Well, it turns out, and we'll prove it next board, that there is no U. Can't exist. It's impossible to exist. And I'll give you a hint. It's sort of like the Barber paradox. Uses that kind of, and Gödel also. Gödel's famous incompleteness proof, well, the second one, but that's the one that's usually referred to as the, even though there's two. Gödel incompleteness theorem also involves that kind of self-referential type problem, like the Barber paradox. If the barber doesn't shave himself, who shaves the barber? If the barber shaves himself, he doesn't shave himself. If the barber doesn't shave himself, he does shave himself. That kind of thing. Alright, so this particular language, ATM, is undecidable. I've got 7 exclamation marks. Okay, I'll stop there and expect a lot of fun on the next board. That's when it gets really meaty and powerful and just amazing.